So this review, as you can see at the top there, is on polar coordinates. So the first thing that I have here is just recalling how to graph polar coordinates, what they're comprised of. So this is always r comma theta, where r represents the number of steps that we're going to be taking from the origin, and then the angle is the angle in which we're going to be taking those steps. So if we were given a polar graph that looks like this, an xy plane, we have one little circle there with a radius of 1, one circle with a radius of 2. What this polar curve is telling, or this polar point is saying, we're going to look at that angle pi over 2, which is our 90-degree angle. This says we're going to go 2 steps in that direction, puts our point right here. And that's pretty much polar. We'll do one more, just make sure we understand some negative ideas. This says look at pi over 2 just like we did. So again, we're looking up here at this pi over 2. But instead of going in this direction 2 units, if we have a negative r, that just means we're going to go backwards 2 units. So look at this angle. But since we're looking at that angle and have a negative r, that means we take 2 steps backwards from that angle, ends up right there. So that's our polar points. That's something we want to make sure we're able to plot, understand. We also did these polar inequalities. These not likely something you're going to have to deal with, or do one of them here. But this is the idea of just understanding the r's and the thetas, how they coexist and how they are allowing us to graph our points and or inequalities. So this is just telling us here first, we're only focused on the angles from pi over 2 to 3 pi over 2. So from pi over 2 to 3 pi over 2, that's all this stuff over here. And then since our r's lie between 1 and 2, that means we would want a circle here that would have had a radius of 1. In this case, a semicircle, I suppose. We would want the same thing for the radius of 2. Since it is an inequality, we want all r's in between 1 and 2 as well. That means we'd want the circle at 1.5, 1.6, and if we want all of them in between here, what that ultimately leads to is us shading all of this in. So it's like a half washer. All right, and then this one, you're just looking between 0 and pi over 2. So these are these angles. And then we want all r's that are negative. So if I'm looking at pi over 2 and I want all r's at negative, I want all of these. If I'm looking at angle 0, but I want to go backwards. So what this ultimately ends up with is pretty much anything in the third quadrant would end up being our answer. So that's how we plot them. The next thing, this for sure will be on there. Sometimes it's obvious. A lot of times it's hidden. So these here that I'm going to do right now are the obvious ones. And then there's some AP questions on the back that they're a little more hidden and a little more sneaky in terms of what they're really testing you on. So you definitely want to know these. What I have right here in this open space is we can always kind of prove these by, let me draw this a little better, drawing a circle that's centered at the origin, and then draw a radius out from there. And then we create this angle. And we can then drop down an altitude to create a right triangle. This is x, this is y. And then from there, we can pretty much create all of these very quickly. Just some simple SOHCAHTOA ideas, or right triangle trig. X is equal to r cosine of theta, because if we look over here at this graph, the cosine of theta is this adjacent side of x over the hypotenuse of r, and then we would just solve that for x. You can get all of those from this little right triangle that we could create within our circle. So definitely know these. This will be something that you're going to be responsible for, that you're going to see. So when we look at this one here, this is an obvious one where they're just telling you to take a Cartesian equation, polar equation, be able to go back and forth. In this case, they're giving you a polar because it's all r's and thetas. Well, if it's going to go from polar to Cartesian, we want to change from our thetas to x's and y's. So if I look at the r squared, the one that takes r squared into x's and y's is the Pythagorean theorem. So that's just x squared plus y squared. And then if we look at our tangent of theta, the only one that we have here is this one, where tangent theta is said to be equivalent to y over x. That is your answer, sort of. Being a multiple choice, we then just have to make sure that we pick the one that's equivalent to this. So if we multiply everything by x, so x here, multiply these by x, you'll get that x cubed plus xy squared. Subtract your y over. Should end up getting an A, or letter A. The next set, these are actually right from our notes. We don't need to be too creative with these, just a little refresher on how to do this. R cosine of theta is an x, so that's a vertical line. R squared cosine squared, same idea where R cosine is x. Well, if we have it squared, that means this is an x squared. R sine of theta, if you look, is a y minus a 3. This one really is an R cosine theta times an R sine of theta. And then all we did to simplify that, we multiplied those r's together, but we could split those into R cosine, and then this is x times y equals 4. And then the last one, this on the right-hand side, definitely 1 plus 2x. And then we just have to decide sort of how can we get that r to be an x and a y only. And that's the same one that we would have used up here, where r squared was equal to x squared plus y squared from just the Pythagorean theorem from that little diagram up above. Take the square root of that. Substitute that in over here. And then that's our Cartesian. You may have to simplify it. Again, if it's for your response, you don't need to worry too much about simplifying. Multiple choice, and obviously we're going to want to try to make that look like our answer. Okay. All right, next one, same thing. Let's go ahead and do x squared plus y squared equals 4x. And then now this one, I'm asking you to describe what this graph would be. Not something I would really anticipate doing or having to do on that test, but just as a little refresher, let's talk about this. If I subtract that 4x over, the substitution should be pretty obvious. We just did a bunch of them on the previous page. This goes into, if you remember all that completing the square stuff from previous years, really. It's really not something I think you're going to have to worry about, just in case. X squared minus 4x, if I want to complete that square, what we did or need to do is cut that in half. That's a 2, and then whatever that gives us, we need to square. If you remember the quilt problems back in the day, completing that square. And then notice how we added 4 out of nowhere on the left-hand side. The reason we do that is to make this now a perfect square. We could say that's x minus 2 times x minus a 2, so that it is in fact a perfect square plus a y squared. But we all know, hopefully, that if I add 4 to one side of this equation, I better be adding 4 to the other side as well. So what we should then see as we look at this equation is that this would be a circle. The center is 2, 0. Since this should be right here is your r squared in the basic equation for a circle, means our r is going to be a 2. So that's what it means by describe it. So what are we dealing with? The next set of problems, finding the derivative of a polar equation. Certainly, again, something that you're going to need to be able to do. As I mentioned when we did this in class, if you want to memorize this, totally valid. You're going to need to know it. So if you want to spend that time to kind of get it down, whether you just through rote memorization or you come up with a little song, whatever. I've seen a lot of different combinations of people memorizing that. That's totally fine. But all you have to really understand is what we're doing is taking dy d theta and dividing it by dx d theta. And where we're getting those from is taking the derivative with respect to x Remember what y is equivalent to? Y is our sine of theta. So all I'm really doing is taking the derivative of r sine theta. So that's why the derivative of r gives you this r prime. Leave the sine theta alone, which is a product rule. Add, leave the r alone, and then the derivative of sine is cosine. And then on the bottom, all we're really doing, if I want dx d theta, remember what x was, it's our cosine of theta. So all I'm really taking the derivative of is what x is equivalent to, our cosine of theta, and that's going to give us this. So up to you. You're certainly going to need to know that. So have a strategy one way or the other. So now when we go to number 12, notice how we need r primes. So if I go to this equation, let's take the derivative of r, which would be the negative sine of theta. And then from there now, we can go ahead and start substituting in. So let's go back to this up here. R primed is what we just found to be negative sine of theta. Then you're going to throw down that sine. Then you're going to see plus r. So I'm going to do plus and then 1 plus cosine of theta. And then cosine of theta. And then all that gets divided by, and then now I'm just going to fill in this stuff right here. So r primed is that negative sine of theta, cosine theta, minus your r is again the original equation, times sine of theta. And then we now want to evaluate this at the angle of negative pi over 2. So throw all those in. Let's see here. All right, so negative pi over 2 is just down here. So that's going to be the 0.0 negative 1. So we're going to get a lot of those coming up. So the sign down there is a negative 1 plus a 1 plus the 0 times a 0. And then go ahead and fill this out. We can do this. Negative 1, another 0, plus 0, negative 1. Yeah, it looks good. So all of these together give you a negative 1. And then this all cancels. Down here, this all cancels. Down here, this would have been a 1 times the negative. So negative 1 times another negative 1. Our denominator should become positive 1. So that slope should end up being a negative 1. All right. Very common question with these also. You were exposed to these. This is with our parametrics and with polar. The idea that it could ask, where do you have a vertical tangent? Vertical tangents mean your derivative is undefined. And if your derivative is undefined, that means this denominator is going to be 0. So we want to understand, you would just take that dx, dr, set that equal to 0. If it asks for a horizontal tangent line, I guess I wrote dx dr, it's dx d theta or dx dr. The reason we have different variables here, just notes the derivative of the x. If it asks for a horizontal tangent line, that means your slope is 0, so now that would mean our numerator is going to be equal to a 0. Then what we end up is a little trig equation. So we did a few of those. It's on your test. Those are things that you want to make sure that we're aware of as well. All right, graphing these. They won't make you graph these. I've never seen that before. Anytime they've asked you to deal with a graph, they've always given it to you. You can go back and look at any old question, and they're going to give you that. So I wouldn't worry too much about this. However, do know that the sine of theta is going to, if it's strictly sine of theta, is going to be symmetric to your y-axis. Cosine of theta is going to be symmetric to the x-axis. Again, graphing one of these is not really something that's terribly important. One of the reasons we do graph it is so we understand how we can get r's of 0, how we get those negative r's, because those give us those little inner loops. Those little inner loops sometimes play a role in the question in terms of finding the area of the inner loops, all of that. So if you wanted to kind of go through this, again, I wouldn't worry too much about this. Here's what this should ultimately look like. The reason I want to talk about this one more so than the graphing of it is so that we understand sort of, let me rearrange this, where the little loop comes from and why we get that. The reason we would get that little loop, if you remember, is that at some point in time, the reason we go right through the origin is because you're going to get an R value of 0. It means you're going to look at some angle, but if R is 0, you don't take any steps in that direction. You're also going to get R's that are negative. So what this really ends up being, what does it end up being? Probably a -1 would be my guess. Yeah. And then those negative R's are the ones that are going to give you the little loop. So what we did a lot of times, we're going to figure out where that inside loop comes from, is setting this thing equal to 0, and then solving this trick equation. So just recall that, be able to remember how to do those. Those are pretty common questions, something that you're going to want to be able to do. We're going to do one here in a second, so I don't necessarily need to do that one now. But that's graphing them. Area. So I'm going to ask you to find the area enclosed by that polar curve. It's from the area of a sector, but this is our little formula. So if I want the area of this thing, we're going to do 1/2 the integration of R squared. R is going to be pretty simple. They're going to give it to you, or sometimes they've given you the derivative of R. We need to figure out R from doing the antiderivative. All right, so depending on what they give you, how are you going to work with that? But we need R to get squared. In this case, I just flat out give you R. So you're just going to plug in 2 times 1 plus cosine of theta. And if we want the whole area, in this case, you're just going to go 0 to 2 pi. Never really seen them try to trick you too much with the period and how many times that this thing is going to reproduce itself. But that then, just throw that in the calculator, that should give you your area, should end up being 6 pi. So when you get that, it's going to be a weird decimal, but if you convert 6 pi into the decimal, or take your decimal divided by pi, it should give you 6. All right, so now here's kind of that big one that we were talking about before. This has an inner loop. So let's say we don't have a calculator in our hand, and we don't want to have to sketch all this out. The reason we get these inner loops is because when we do our little chart, for the sake of graphing these, as we were to do all of these, at some point, we get an R value that is a 0, so we don't take a step in any direction. And then somewhere we start getting these negative R values until we get to another R of 0 where we don't take any steps. So what we did is we figured out, when does R equal 0? So in the equation, we let R be a 0, and then we solve this. So cosine of theta is equal to a -1/2. And then what we're now thinking is, on our circle, what angle, so what we're solving for the theta here, that's the variable in this equation. So what angle has an x coordinate of a -1/2? So we have to be in these 2 quadrants because that's when our x coordinates are negative. And then the angle where we get x values are your pi/3s. So normally here's pi/3 in the first quadrant. That's 1/2 and then √3/2. So what we want is the pi/3 angle in the second quadrant, which is 2 pi/3. And then this pi/3 angle in the third quadrant, which is 4 pi/3. The same formula, 1/2 and then the R squared times our d theta, and then the d theta is your limit. So we actually put the difference in the angles as your limits. So we want to go from 2 pi over 3 and then to 4 pi over 3. All right. And then plug it in your calculator. Just be careful. Don't forget the squared. That's common. And don't forget this 1/2 out in front. All right. Next one we're going to do. Don't worry about 16. That, again, is just not something that they're going to try to get you at. 17, find the area enclosed by this one on the interval of 0 to pi over 2. This is a non-calculator question. It's kind of want to expose you to this. It's because it's been hard to really test non-calculator ideas this year. So I just want to make sure we're kind of understanding what this is asking. So it says the area enclosed by this curve on the interval of 0 to pi over 2 is what? We don't need to know what it looks like. As soon as they tell us that we're finding the area of a polar curve, we know that we're setting up 1/2 the r squared d theta. So we can get r by solving for this. So divide that over for r. Then we could use this, so we can definitely put that in here, but it's going to look weird. So what I would prefer that, or what you would need to know how to do, not what I would prefer, what you really need to understand, 1 over cosine is a secant. So I'm going to rewrite this as secant. I'm going to do theta over 2. That's what I'm going to plug in here. Secant of theta over 2 all squared, which is how this is currently written. Isn't that then the same as just taking this little squared and writing it right here? And then a secant squared should be something that's familiar to us in terms of us being able to take the antiderivative. That's why we would need to recognize 1 over cosine as that secant. We also don't need to know the graph because they're telling you what your limits need to be. They're telling you just let this be 0 to pi over 2. Don't really think too much on that. And then now this is something we should be able to handle without your calculator. So when we do these, this goes back to our discs, our washers. Simplify the integral first. So that's what we have now done right here. Then take your antiderivative, and now we can do that. So the antiderivative of secant squared is tangent. Leave the inside alone. But then we've got to divide by the coefficients. So that's a 1/2. And then you're going to evaluate that from 0 to pi over 2. If you notice, the halves are going to cancel. We had the 1/2 in front. We just divided by a half. So all we really now have is that tangent. So we're now going to plug in the upper limit of pi over 2 divided by 2 minus the tangent of, this would have been 0 divided by 2, so just a 0. So what we're really looking for is the tangent of pi over 4, which is a 1, minus the tangent of 0, which is 0, giving us D as our answer. All right. The next type, what if we need the area in between multiple curves? Again, they have always given you these. Your ability to graph on a calculator in Polar is not something they'll test you on. And there's just no way they're going to have you do this by hand, graph these by hand. So they would almost certainly give these to you. So because of that, here's what they look like. So one obviously is a circle that we know has a radius of 2. And then the other one should be circular also, somewhat up here. Let's say they just gave us those. Just looking at this here, we would know that this is the equation of r equals 2. By default, then, the other one has to be the 4 sine of theta. What we then want, remember I would label these as area 1, 2, and 3. This one is asking you to find the area inside of that 4 sine of theta, but outside of the circle. So in this instance, we are looking for area 1. So we still have our 1/2. But now we have two different ones. So we want the bigger r, and the bigger r is always defined by the one that's the outermost, minus the smaller r, and that would be the one that's closest to the origin. So that's your inner graph. So if we look here, if this is where we're always standing, where we're always oriented, if we're looking off in these angles here where these two graphs exist and we're looking for the area in between, what we need, I may have to plug in here in a minute. All right, let's finish this one and then I'm going to have to plug in my computer so I don't die, is what angle do they intersect at here? And then these are all the angles in between. And then what angle do they end at? All right, those are the two elements we need. So the outer term, we know, 4 sine theta. And then the inner circle, the smaller circle, or the smaller curve is the circle too. Set those equal to each other in order to figure out where they intersect. So you're going to do 2 is equal to 4 sine theta. So we're now looking ultimately for the angle whose y-coordinate is 1/2. So over here, isn't that at pi over 6, where we're root 3 over 2 comma 1/2? And then that would mean we want the pi over 6 angle in the second quadrant. So we're going to go pi over 6. The pi over 6 angle in the second quadrant is 5 pi over 6. That is your setup. And then again, throw that in the calculator, being really, really careful how we plug that in. Even with me, this is what I got, but easy to screw this up. I probably should have threw that in a couple of times just to make sure. But that's your setup. Okay. If you wanted to, number 19 I feel is a tricky one. So if you wanted to try to think on that one a little bit, I need to plug in my computer before it dies. So give me a minute here, and then you could think on number 19 or just pause me. Actually, maybe I just pause this. Let me see. Okay, I'm back. So with this one, if we were to go ahead and graph this, r equals cosine of theta is going to look like this. And then 2 cosine of theta should just pretty much look like the same thing, right? Except it's going to be a little bit bigger, twice that size. So it kind of looks like this. All right. So now what we're looking for is we want to be inside of the big one, but outside of that small one. So normally if you had a little time, I tell people to kind of look through this one a little bit, see if you can't figure out sort of what's going to be going on here, because it is a tricky one, the way that they have this set up. If we kind of look at how all these answers are written, so what I was getting to, if you want to try this on your own, feel free. Notice how most of these have 0 to pi over 2. And then this one's 0 to pi. You can always be assured that if all of these are 0 to pi, and then there's one random one, it's not the random one. So I wouldn't worry about E for sure. That's just a general rule that you kind of want to follow on the AP test. So it's got to be 0 to pi, which is weird because they're not making us go all the way around. So if we start with the premise that it has to be 0 to pi over 2, then that's important to understand that 0 to pi over 2 is only going to give us half of this full circle. If I start at 0, cosine of 0 is going to give me this 1 right here. If I go to pi over 2 in this one, that's going to give me that first r of a 0. So when we do this, it's just giving us this first half. So that we want to understand that if I did 1/2, let's do what we know. This obviously has to be 0 to pi over 2. The outer curve is the twice cosine of theta, and then square that. The inner curve is the single cosine of theta, and then square that. This is our setup. that would give us, let me show you what that simply gives us. It gives us that area from 0 to pi over 2 only. So notice too, we want to clean this up a little bit, but what we could also understand then, if that's only going 0 to pi over 2, isn't that only giving us half of this region? We still need all of that. So what we would want to do then ultimately is take this, and then we would want to double the value that we would get from 0 to pi over 2. So that as these now cancel, what we're really looking for is 0 to pi over 2 of all of this that we now just need to clean up. So square those. End up with some like terms here. And then that should end up being our answer. And now I'm having a little deja vu because I do remember this one from last year. It's A and B, if you notice. Interestingly enough, those are the exact same answer. So that's either one. All right, circle which please. All right, 19. Let's see here. 5 is a circle of 5. So there's your circle. And then the other one should, I go through 4 here, and it does this. We want outside of the circle, inside of the other one. So this is our region. So here's why I'm giving you these. This one is this is a nice one where you're going to do your outside curve. So that is this 5 minus cosine of theta. The one that isn't a circle with a straight radius of 5 everywhere. Square that, and then we're outside of the circle, squared. So that we've now done a couple of times. It's not a hard concept to understand. When we go to find our limits, here's why I want to do 20 and 21. We're going to set those equal to each other for sure. What we ultimately end up with is the cosine of what angle is going to equal a 0. So it's kind of obvious based upon the graph. If we look at the equation, it reveals itself the same exact way that we get x coordinates at pi over 2 and 3 pi over 2. So if you think about where those angles are at, here's pi over 2, here's 3 pi over 2. If I want all the angles in between, so here's pi over 2, these flow in the right direction. We do want all the angles between pi over 2 and 3 pi over 2. All right, pi being the most obvious one. So if I start at pi over 2, go to 3 pi over 2, it's going to give us the shaded area that we're ultimately looking for. Where that is different is in number 21. So if I now go to number 21, let's graph this. We have a circle with a radius of 1. Sketch that in. And then that 2 cosine of theta looks like this. You're then told we want to be inside of the 2 cosine of theta, outside of the circle. So that's this one. This is our area. So once again, the whole outside minus the inside, we hopefully have a pretty good handle on at this point. We have done this recently, and today we've done it probably the 4th or 5th time already. The outside curve is that 2 cosine theta. The inside curve is the 1. If we then set those equal to each other to figure out where they're going to intersect, at what angles they intersect at. In terms of this equation, the cosine of theta equaling a 1/2. So again, what angle has an x coordinate of 1/2? That would be your pi over 3's. So in the first quadrant, that's a pi over 3. And we are down here in the 4th quadrant, so our first thought probably is 5 pi over 3. But what you have to be careful of, and we didn't have to deal with it in this one, but if you now look at this one, if I go pi over 3 to 5 pi over 3, what that would be telling me, let me change color here. If I'm going to start at pi over 3, the first angle I'm looking at is this one. And then I want to go in order to 5 pi over 3. That means I'm actually doing all of these angles here. And there's no area, as we eventually hit 5 pi over 3, there is no area shown between pi over 3 and 5 pi over 3. So we have to just understand that sometimes our limits aren't quite what they seem. What we need are all the angles. Let me put my axes back in here. That's bad. There we go. That run from here to here, and we need to go in the correct order. So this is one of the ones, yeah, this is still going to be pi over 3, but we want to rename this 5 pi over 3 as a negative pi over 3. So if we now think, if I go back to these, if I now make this negative pi over 3 to a positive pi over 3, if I start at negative pi over 3, notice how I would then get the 0 fits in there nicely. Now we're working through all the angles that would give us that area in between, the yellow area that we have shaded. All right. So that's something to be careful for with these, is just make sure we're going in the correct domain in the direction that those polar curves would be getting drawn. All right. All right, the next page is, hold on, let me pause this, because these are now our AP. All right, sorry about that. I had a version that didn't have these AP questions on there, so just added those. So on your next page, you'll see this guy. It's a question from a few years ago. Like I've mentioned before, when they've given you these graphs and ask you to work with them, they've always given the graph, so just further evidence of that. The graph of the polar curve, and then they give you this, and they're telling you that's on the interval 0 to pi, as shown above. Let S be the shaded region in the third quadrant, bounded by the curve and the x-axis. So what we're looking for there is then, instead of the inner loop, they're asking for half of that inner loop. So what we want to understand, for sure, we're going to be setting up, we're looking for an area, right? So there's no doubt we're setting up this 1/2. We're going to be doing an r squared. Like we just hammered out a bunch of those on the previous ones, the ones that are not the free response questions. We know what r is. It's 1 minus 2 cosine theta. So that's pretty straightforward. What we need to figure out are the limits. Like, what are these limits going to be? So what we have to understand is, and this is why we do graph these all out when we first do them in the notes. You never will have to actually produce that graph all the way around. But when we do that, it's easy then to see why we're hitting the origin right here. Because when we do those little r theta charts, the reason we're right here is because we have an r value of 0. The reason we're right here is because we have an r value of a -1. So those are the keys. We need to figure out, when does our r have a value of 0? When does our r have a -1 for the value? So we're going to take the r value, or the r equation, and we're going to let it equal a 0. Because when we figure this out right here, that's going to tell us what angle we start at the origin with. So what does that give us? Cosine of theta. So it'd be 2 cosine theta equals 1. So we're looking for the cosine of theta to equal 1/2. That happens at 2 different places, at pi over 3 and then 5 pi over 3. Okay, we'll differentiate in those here in a second. The other place we want to know is, where does it equal a -1? So let's take that r equation, set that equal to a -1. So now that is what, -2 plus -2 cosine theta. So we're looking for when the cosine of theta is equal to a 1. What is that? So what angle whose x coordinate is 1, and then nicely that's going to be 0. Now, it's also 2 pi, right? Same down here, pi over 3 to 5 pi over 3. So how do we kind of tell the difference? How do we know which one for a fact we are? We could fill this whole thing out and start to sketch this. That would be a process. That's something we don't necessarily want to do. The way we can really focus in on which one of these two do we want, which on one of those two do we want, is just the interval that you're given. Don't our angles all have to fall between 0 and pi? So the only one of these that fall between 0 and pi is pi over 3. And then the same down here has to be the 0. So these limits would have to be 0 to pi over 3. My guess is, if I don't remember what number this is, this probably would have been non-calculator. That's why they're just having you write the integral expression. You're not having to evaluate it. All right, and then that simply is your answer. Letter B, I mentioned earlier that sometimes it's obvious when they want you to convert from polar to Cartesian or back from Cartesian to polar. Sometimes it's a little more hidden. That's what this one is. When they ask you to find dx d theta, only way we're going to be able to figure out a dx over a d theta is if we have an equation where we have, x set equal to a bunch of expressions in terms of theta. So if I had this equation here, where I have x on the left and it's written in terms of the variable theta, then the derivative, I could write this as I'm calculating the change in x according to my change in thetas. So in order for us to find this ratio, we need an equation written specifically in terms of x and thetas. Okay, not sure what's happening there. So this then gets into our conversions. So let's write the two things we know. This is given to us. And then we also know, conversion-wise, if we're talking about x, that x is equal to r cosine of theta. So then how can we use that? If we just want x's and thetas, we need to get rid of this r, right? So we could just say x is equal to, let r equal what it is equivalent to in this particular problem. And then now don't we have an expression for r's and thetas? The other way is understanding that if we take that conversion, x is r cosine of theta, solve that for r. So then we come over to this version. Let's get rid of r with x over cosine of theta equals 1 minus 2 cosine of theta. But if I now solve that for x, wouldn't I take that cosine of theta right here, multiply that over? And when I do that, notice how either route we take, we get the exact same equation. So whichever you see as the easier route to take, whichever one you just visually see quicker and makes more sense to you, is totally fine. The big issue is making sure we understand that's what needed to be done, that's how you're going to convert them. From there now, I think, let me go back to the directions. You're just going to write expressions for these. So we do need to ultimately take the derivative. We still have to do this one. We'll do that one here in a minute. We now just need to take the derivative of the dx d theta that we have. So dx d theta, this is a product rule, first term, second term. So the derivative of that first term would be what, 2 sine of theta? Leave the cosine alone. Plus, leave the first term alone. And then the derivative of the second one would be a negative sine of theta. Do not even think about simplifying that. They're going to be completely happy with that as your answer. So just leave it. When we go to dy d theta, same idea. That if you're given r is equal to 1 minus 2 cosine of theta, and we know that x is r, that y is r sine of theta, then it's whichever you prefer. You can get rid of r right away by taking this and plugging it in for r, and you have nothing but y's and thetas. If you like that version, then go with that version. You could solve this for r and then get rid of the r right here with y over sine of theta, and then you have nothing but r or y's and thetas. Really up to you how you want to handle that. I am going to do this one. So y equals r sine theta. What was r. 1 minus 2, oh, it's right here. So I'm going to take what r is, which is, it's told right here, to be 1 minus 2 cosine theta, and then your sine of theta, and then just take the derivative of this. So dy d theta, product rule again. And then product rule, you're going to add, leave the first term alone, and then the derivative of sine is cosine. All right. So then that's B. Then we go to letter C. It says write an equation in terms of x and y for the line tangent to the polar graph at theta equals pi over 2, and then show the computations that lead to your answer. So writing the equation of that line, we've been doing this all year, not necessarily with polar, but certainly writing the equations of lines. And what we always know is to write the equation of a line, we first need to have an x and a y coordinate. And then the second thing we need is our slope. So those are the two things that we're now concerned about. For our slope, isn't it dy d theta divided by dx d theta? Don't we already have those, right? If you look up at letter B, we've already found dy d theta. We've already found dx d theta. Now we haven't evaluated it yet at a particular angle, which is what we're going to need to do. But don't we have those expressions? So this is dy d theta right here. And then this is the dx d theta right there. What we now simply do is evaluate those. So I'm going to go ahead and just do this using this one here. So let's evaluate dy d theta at the angle of pi over 2. So I'd have 2. The y coordinate at pi over 2 is a 1. Y coordinate at pi over 2, 1. Then I have the plus. Then I have 1 minus 2. The x coordinate at pi over 2 is 0. And then another x coordinate at pi over 2, which is a 0. So what do we end up with here? Just 2. Your denominator should be dx d theta. Like I said, that's this up here. So I'm going to have this 2. The y coordinate at pi over 2 is a 1. The x coordinate at pi over 2 is 0. And then plus 1 minus 2 times the x coordinate, which is 0. And then this is a negative sine of theta, so that should be, what, negative 1? So these will go away. This ends up being a 1 times a negative 1. So our slope should end up being negative 2. The last thing then is we need our point. So x, y. So again, they're just asking you to be able to convert. We know x is our cosine of theta. And we know y is our sine of theta. So just plug what those are, or what r is. So r is the 1 minus 2 cosine of theta times a cosine of theta. Just a little more room. And then y is the r multiplied by the sine of theta. And then we just now need to plug in pi over 2. So if I know x at pi over 2, again, cosine of pi over 2 is a 0. So we find that our x coordinate is 0, so that's always nice. our y coordinate at pi over 2 means we'd have 1 minus 2. The x coordinate at pi over 2 is again a 0. But then when we do the y coordinate at pi over 2, it is a 1. So this would become a 0. You have 1 times a 1. The y coordinate is a 1. So this was our slope. We now have our point. And then that's our answer. Last but not least, this one we've actually have done. So if you don't want to listen to me anymore, you could go back to our notes and do this one. I wanted to do this one again because to me this is a good question that makes you find this little middle region in here that a lot of people have a harder time with, and I did want to review that a little bit. And sometimes I honestly forget what I have in the review packets when we're going through the chapter. There are a few of them that have this, but this is what's in our packet, so this is one we'll do. The graphs of the polar curves, so r equals 2, we know is the circle, and then 3 plus cosine 2 theta is the non-circle, and then they're giving you where they intersect. So if you wanted to try A, see we can now do this, because this is where, if you remember when we were doing them earlier today, we talked about 1, 2, and 3. If I give you 1 and 3, those are the nice ones. Region 2 is the one that requires usually multiple little setups, sometimes multiple integrals, sometimes the area of, in this case, a circle minus another integral, things like that. It requires a little bit more thought. So if you wanted to try to figure that out, but what they're asking you to do is find this, include the area that's shared by those two, that region R, the area that we would have labeled as 2 when we were doing these sorts of problems in that chapter. So it says that R be the region that's included. Find the area of R. You know, there's a couple different ways. The way that I think is the easiest is to take this circle and know how to find the area of a circle. So if I did the area of the circle, pi r squared, this circle has a radius of 2. So we know that the area of that circle is a 2. That, however, gives us everything as being shaded. And that's obviously not what we want. What we don't want is that region that I just drew in. So what we don't really want, let me go back to labeling these as regions 1, 2, and 3. Don't we really want to get rid of that region 1? We don't want that shaded like I wanted. That then is the types of problems that we were doing earlier. I would then subtract, and then this goes into the whole area in between two polar curves. If this is now the area that I'm looking for, which it is, I'm just going to be subtracting it, but this is the area that I want. I've got to do whichever curve is on the outermost part of that, which is the circle, squared, minus the inner curve, which is the non-circle, the 3 plus 2 cosine theta, squared, over the interval that you were given. And this is told to be 2 pi over 3. And then the second one you were given is 4 pi over 3. No tricks here. This is the direction that we want to go. So this becomes our lower limit, the 2 pi over 3, and then the upper limit becomes that 4 pi over 3. And then whatever that gives you, we then subtract away. Oh, then I'm going to pull that key up. Shoot. So throw that into the calculator. Whatever that gives us is our answer. The other way that you can do this, just in case it doesn't work out this nicely, is you could also deal with the idea that if I just go from here to here and go in this direction, notice how the circle, if we're going in this direction, we could set up an integral for the circle. So do your 1/2, the circle is just 2 squared, and then our d theta. And then this here, now you do have to be careful with your angles. If we want to start here, moving in the proper direction, we would want to call this a negative, what do we want to call that? Negative 2 pi over 3 is the negative angle down there, to the positive 2 pi over 3. So what that now does is that gives us all of this. And then we would now add the area of this, I don't know what you would call it, and we call it cardioid, it's close enough. So that's going to now be 1/2. And then again, you're going to do your r squared, so we know that's going to be the 3 plus 2 cosine theta, d theta. And then that, we would want everything in here. So the cardioid is bounding us from the 2 pi over 3 through the 4 pi over 3, all right? All the way through here. And then now we would actually add those two together. I can make this nice and black so we can kind of see. So the cardioid is bounded, or is the curve that's including this area. And in this instance, you would add those. So there's a couple different routes, but typically when you have to find that shared region, you're definitely setting up multiple integrals. Or if you can do a simple geometry shape like this pi r squared version, that's the two parts you're going to be dealing with, the circle part and then the integral part. So I want to make sure we saw that. I want to make sure we reviewed that real quick, just in case that's something that we need to be able to do here next week. 3, letter B, particle moves with a non-zero velocity, polar curve given by. This is, again, as we look at this, one of these ones that's kind of hidden. So what this is telling us is the curve, or the particle moves along the curve, so that dr dt is equivalent to dr d theta. And the r that we're dealing with is this one. So I could right now take the derivative of this equation and get a dr d theta. We can do that. All they're telling you is that dr d theta and dr dt are equivalent to each other. They're one and the same. So when they say find the value of dr dt, it's the same as finding the value of dr d theta. So all they're really asking us to do in letter B is to take the derivative of this, because dr d theta is the same as dr dt. They're telling us that right here. So we would take the derivative of this. That's a simple little negative 2 sine of theta. We want to evaluate it at pi over 3. The y coordinate at pi over 3, root 3 over 2. So this would be a negative root 3. What they're then asking you to do is interpret this. Again, we've done this, so hopefully this is familiar. Hopefully we can think this through right now before I say what this is to interpret your answer in terms of the motion of the particle. So what they're really focusing on, what they really want you to understand and explain is, do we understand what these ratios mean when we find them? That if I did the change in r over the change in time, what does that mean with respect to the motion of this particle? So what r always stands for in polar is the distance from the origin, and then the time is going to be your t. So what this is saying, if my dr dt ends up being a negative 3, that means that the curve would be approaching the origin. The curve is getting closer to the origin, or your r's are decreasing as our time is passing. All right, so that's kind of what we wrote out, is that the curve is getting closer to the origin, all right, at the time of pi over 3. And make sure you do say at the time of pi over 3. C is similar, a little sneakier, because they now want you to find dy d theta. There is no y at all in the equation that you are given here. So this then is one of those little conversions without them coming out and saying it's a conversion. We need to get an equation with y's and thetas exclusively. We know that y is r sine of theta. So if I want to get rid of this r here, we know r is equal to y over sine of theta. So if we're going to do that substitution, and we now know y, if I multiply that sine over, is equivalent to this. Now if I take the derivative of this, I can say that this is in fact a dy d theta. Another little product rule here. So derivative of 3 is 0. This would be a -2 sine. Leave the second term alone. Product rule we add. Leave the quantity alone, the first term alone. The derivative of sine is cosine. We then want to evaluate that at pi over 3. All right, so sine of pi over 3, oh gosh, is root 3 over 2. And this one, cosine at pi over 3 is our 1/2. Goodness. All right, what's this going to give us here? So -2 times 3/4. And then 2. So oh God, hope I didn't screw this up. It's at 1/2. All right, hopefully it's 1/2. I didn't pull this up. All right, then you're asked to explain that. So let's assume that Mr. Pena did not screw this up. What this is now asking you to do is justify what dy d theta is. And again, remember what dy d theta is. It's equivalent to dy dt. That's why it's the motion with respect to time. If our y is changing, what that means is we're moving up and down. So our vertical position is changing. So when it asks, how does this get interpreted in terms of the motion of the particle? What we said with this one is if we're moving up and down, well, we're moving farther, in this case, oops. So this was our 1/2. Most importantly, this is a positive 1/2. So what that means is our vertical position is changing. So what that is telling us is we're moving farther away from the x-axis at the time of pi over 3. So hopefully that makes some sense. Polar has become very popular as a free response question here in the last 10 years. It had never really been on there the first 10 years of doing this, at least for me. And then now within the last 10 years, it's on there almost every other year. It's a pretty common free response question. So look that over. There's not a lot of surprises with them. There's not as many things to worry about with Polar. Everything in this packet has you covered in the types of questions that you will see in regards to Polar. So if you know this pretty well, should be in pretty good shape for this type of a question. All right, signing off. We'll see you guys next time.